Before we kind of get into the Appalachians, which, by the way, like many mountain systems in the world, are very complex and were formed not just from one mountain building event, but from several. The Rockies are very complex too, but aren't nearly as old and haven't been formed by nearly as many processes. The Himalayas they've only been really formed by one ongoing process, and we understand them pretty well, though the Appalachians, because they're so ancient and they've been so eroded down, we can actually see into the heart of them and really get a good idea of some of those really deep-seated, very high pressure, high temperature metamorphic rocks that we can't see in the Himalayas today because we can't see into the heart of the Himalayas. They're forming right now. We're only seeing the outside portions. So seeing the inside of the Appalachians is very special. So not only do the Appalachians tell us a very complex story that spans a billion years of time, but they also give us a lot of evidence for how mountain building forms, for how mountains form, not just the Appalachians. So kind of just start out talking about a few different terms. So I had this picture of some geologic provinces. The first term we're going to talk about are orogenies. So this is something I probably used a little bit back when we talked about metamorphic rocks, but an orogeny is an episode of mountain building, to put it simply. And a body of rock that forms as a result of an orogeny is called an orogen. The process by which orogenies occur is called orogenesis. All right, so there's a lot of weird words there. We'll see them on the next slide. But I like this picture because it, of course, is looking at the whole Earth, because that's what geologists tend to do. And we're looking at how all these bodies of rock form. So some of them are orogens formed by orogenies. So everything in kind of like this tropical, like a seafoam greenish bluey color, are basically ancient or ongoing mountains. So some of these, like the Himalayas, this is an orogeny that's occurring right now. Some of these, however, like the Appalachians, are an orogeny that occurred a very long time ago and are no longer being built any further. Alaska, the whole west coast of North America, a lot of that's still being built. Some of it's kind of dormant. But we're kind of outlining something interesting here, and that is that I'm more or less outlining plate tectonic boundaries as I'm outlining my orogenies. So that's not a coincidence. Mountains occur just like volcanism and earthquakes, mountains are related to plate tectonic situations, are related to when plates generally collide together and can either just form big collisional systems like we see with the Himalayas and part of the Appalachians, or subduction zones where we have diving down of probably the oceanic crust below a body of continental rock, like the Andes Mountains here and much of the Rockies and also part of the Appalachians. So the Appalachians are formed by a few different things. Other ways that bodies of rock that we see on the surface formed are, let's go over here to our local rocks, a basin. So this formed when we had some higher rocks forming over here in the Appalachians, and then during this time period, it became an ocean where sedimentary rock was deposited from an ancient sea. We also have places called platforms that are kind of similar, and a lot of those will also extend out into the ocean a bit. Igneous provinces, this is the Siberian traps. Iceland is nothing but a bunch of igneous stuff because it's a volcano, a whole bunch of volcanoes. Okay. So these igneous provinces will be formed from when we had just a lot of volcanic activity in one region for some reason. And here in India, we've got the Deccan traps too. So both of these actually are correlated to big extinction events. The Siberian traps to the Great Dying 250 million years ago. The Deccan traps, not a tight correlation, but somewhat, to the extinction event of the dinosaurs 65 million years ago. And then more currently, we've got Mount Kilimanjaro and the East Pacific Rise. Oh, I could just draw on this all day. There's just so much going on. I won't, because you're going to get bored real fast. But anyway, lots of things going on. The extended crust is both, this yellow stuff is mostly dealing with bodies of rock that have, and in some cases still are, uplifted above the sea, but have been below the sea. So Repeatedly, they've been below the sea, above, below, above, so on and so on. And then the shield, you know what that is? This orange, this coral color orange, this is going to be our ancient, primitive, original parts of each continent, our continental shields, or croutons, like I said once. Okay. So orogenies, they're forming, they're not only going to build up and vertically and form mountains, they are also building laterally onto continents. We wouldn't have much of the West Coast at all if it wasn't for this process of plate tectonics and mountain building. Our continents would be a lot smaller if it wasn't for these side-to-side motions of squishing rock up onto other rock. Okay, so some of these terms, I know there's a lot here, but you guys have access to this PowerPoint without my face on it, so that'll be nice for you as well. But actually, I think I can get rid of myself. Oh, nice. Okay, I might do that. That helps a lot. Okay, so an orogeny, again, episode of mountain building, and we're usually dealing with continental collisions. We're dealing with continents colliding together. We may have subduction, we may not, but we're getting mountains building higher and higher, but we're also building laterally onto the sides of continents. Excuse me. Oh, wait, I got a little, I think my voice will be a bit better. I forgot to use a headphone. Okay, cool, that might work. Anyway, so I wanted to add a couple other things that are going on here. We are also talking about a process called the Wilson cycle. Now, the Wilson cycle is a model of basically how continents form and then break apart and form again and break apart and form again. The Wilson cycle appears to kind of operate about every 500 million years. So that's why supercontinents tend to occur about every 500 million years. But every place is in their own kind of, every continent's kind of on its own schedule. Africa right now is beginning to, well, it's already several million years, several tens of millions of years in its process of rifting apart, whereas North America is just kind of sort of thinking about rifting apart. Other places like India into Asia are definitely colliding together, and there's no thought of rifting apart at all. So this isn't necessarily a global type of cycle. Every continent is kind of dealing with its own processes here. Okay, so get myself back up a bit. All right. Okay. Anyway, so the Wilson cycle is when we have a big continent, like we talked about back with plate tectonics, we can tend to get some rifting occurring because there's a lot of heat welling up underneath that continent. And that heat is going to begin to form, some magma. And that's what we're going to kind of get as the continent begins to rift apart. Then we're starting to form a narrow sea. So this is what's happening right now in Africa, where we have the East African Rift Valley. We're forming a narrow sea, the Gulf of Aden and the Red Sea. And eventually, a body of that oceanic crust can become so dense and so heavy that it begins to sink down below adjacent continental crust. This can begin a subduction zone. So now we have subduction, and we're getting volcanism, we're forming mountains, and eventually that whole narrow sea may close as this body of rock gets closer to this body of rock, and now you have a collisional event, and you're forming a big old fat continent again. Well, once again, heat's going to well up underneath of that and begin to rift it apart. So this is the Wilson cycle, and we see several bits and pieces of the cycle in the formation of the Appalachians, as well as many other mountains in the world. So I like this image a lot because it kind of, it shows where these different things are happening globally. So going back to the East African Rift Valley, a juvenile system of spreading here, where we're starting to form some rifting, and we actually have a narrow sea forming. This is the Red Sea. So we have some, some stretching here in the southern part of it, but then we're getting a narrow sea forming. Where that process continues is kind of here. No, sorry, this is the mature one. So now the oceanic crust is sinking, it's heavier, it's sinking deeper into the mantle, and eventually you can start to get a subduction zone beginning. We actually suspect that this is occurring along the So it's occurring here. But we also suspect that it's going to occur, not in our lifetimes, of course, but somewhere along the east coast of North America, where we think that the oceanic crust, this is very, very old. This is like 180 million year old oceanic crust, which is about as old as oceanic crust gets on Earth, because that's how old the oceans are. They're not much older than that. And so this is very old, very cold, dense crust. So we think it's sinking to the point that North America may begin to encroach on this part of the Atlantic Ocean and start a subduction zone, which would reinvigorate the Appalachians and get them to become volcanic and continue forming higher and higher. So that's kind of an example of how we're not in the middle, I don't know where we are, but a whole lot of Wilson cycles have gone through and formed what we see about the Appalachians, but this is still an ongoing process, and we could think about what the future is going to be like by looking at the past, which is pretty cool. Okay, so that's how we start to get a subduction zone forming. We start to get some heavy, dense crust sinking down. So now we're getting our subduction zone occurring. So a good example of that is in the Mediterranean with the Alps. Sorry, I don't know which one comes first. Okay, yeah, I guess this one comes first. And so we have some subduction going on, and then finally we are getting more subduction and forming really tall mountain systems like the Andes. And eventually we're going to get a collision. Once this occurs, there's going to be another body of rock. Oh, I'm sorry, I guess this is the next, this is this one, then this one, then this one. All right. So we have another body of rock getting closer and closer to this continent, and eventually they're going to collide, and now we have a continental collision. Well, that's a big bunch of continental rock that's not really letting heat well up out of it very easily, so heat's going to build up. Eventually we'll start to get some magma forming a rift, and we're starting all over again. So, no, this one, sorry. And then this. All right, yeah, okay, kind of making sense of it. The point is that we can see bits and pieces of the Wilson cycle, different parts of the story of this cycle happening all over the world today and ongoing. And we could use that to try to tell how ancient mountains formed. So what I want to get into is, what are the Appalachians doing? So the Appalachians date to more than 1 billion years in age. Some of the rocks that we see in some parts of western North Carolina date to about 1.3 billion years in age. So some of those rocks began to form a long time ago and have been thrust up into that orogenic system. So we have a lot of folded and faulted marine sedimentary rocks. We have a lot of volcanic rocks as well. And there's going to be some metamorphism because there's a lot of heat and pressure, and pieces of ancient ocean floor. Basically, you have everything going on in the Appalachians because there have been so many different mountain building events occurring to form them. So the first event that began to form the Appalachians, it kind of marks the first of several collisions that would eventually result in the formation of Pangea. So when we first start talking about the Appalachians, we're actually talking about another supercontinent called Rodinia that is about 500 million years before Pangea. Then, so we have several events and then Pangea forms. Okay. So we're also not just talking about the Appalachians, we're also looking at the Anti-Atlas Mountains and a few other mountain systems in the world that are now separated by the Atlantic Ocean and other ocean basins, but they were once part of the same mountain system. So first, going back to the Proterozoic, this is the time period we're looking at now, I think, still with Story of the Earth. We're still looking at, well, yeah, definitely now. We're still looking at prior to the onset of complex life. So about 1.3 billion years ago, we start to get a bunch of these cratons, a bunch of these continental interiors colliding together. And 750 million years ago, this culminates in the formation of a supercontinent called Rodinia. Now, Rodinia was not the first supercontinent, certainly wasn't the last, that was Pangea, but it was, I think, like the fourth or something like that. But there have been several that have been together, some have been together at the same time even. So this is showing us some of those rocks that date from this Grenville orogeny. Some pre-existing mountain belts going on in here too. Australia, again, as you guys know from reading about the Jack Hills zircons, are some of the oldest, have some of the oldest rocks on Earth. as well as some here in the Canadian Shield. So check it out with North America. Here's our Great Lakes, which by the way weren't even thought of at the time. We're a billion or more years away from being thought of. But they show that to give us an idea as to how North America is oriented. So like Kentucky, northern Kentucky, Cincinnati area would be here. California, which by the way has also not even been thought of, would be over here. Florida, which has not even been thought of, would be here. So see how everything is oriented. If we had Mexico, it'll be, none of that stuff's built on yet. So showing us that North America is rotated, okay, show my hands this way, see, rotated around this way. And then eventually it's going to rotate this way, but they don't just stay the same way that we're familiar with. And I think that's kind of the cool thing about geology is we're learning to see the world in very different ways than most people do. Learning to see that continents are not permanent things. They seem like it. We walk on them, we build our buildings on them, we think they're permanent, but they not only have they moved across the globe, but they've been very different shapes and sizes, and they've been rotated as well. Okay. So a little bit more about those rocks in Rodinia. Let me get rid of myself there. So we have a lot of igneous intrusions, as these mafic dikes are all about. Some words here, anorthosite is a rock they're actually mentioning in some of the story of the Earth. I believe it was chapter 4 where they talked about anorthosite a lot. This is a rock that's not terribly common on Earth, probably doesn't form a whole lot anymore, but formed during part of the early history of the Earth and is the rock that largely makes up the moon. And then as they've been talking about in our book, those experiments where they go from olivine in the mantle and then creating anorthosite or pyroxene as what we see much more commonly on Earth. So we have an understanding of how that rock forms. So we have some sedimentary basins. All right, those are not going to be too important, but our Grenville rocks here. And a lot of these are still shown today in the Appalachians. So very, very ancient rock dating to over 1 billion years in age. Okay. So I want to show you a little map of the Appalachians. So this is a very complicated map. We have all these different ages. So Precambrian is kind of time period that we're dealing with. Anything older than about 540 million years, which is going to be, almost about 88% of Earth history, right? And then we'll talk about what's happening to the Appalachians through the Paleozoic. Then finally, Pangea forms right about here and is the last time the Appalachians have an orogeny. And then what happens to the Appalachians throughout the Mesozoic and then more recently. Okay, so we're kind of seeing where rocks of different ages are exposed in the Appalachians, not just there, but elsewhere. So we can go over to Cincinnati. By the way, I can kind of see the deposits or the, erosion of the Licking River and the Ohio River. So I know here in northern Kentucky, we are right about here. To put that in perspective, Lexington is here, right? Cincinnati is like there. So we're on our ancient Ordovician, a late Ordovician rock. Okay, remember those fossils that we saw with our sedimentary rocks? So that's kind of what we're looking at. Younger and younger rock as we go out. And then as we get into the Appalachians, which are mostly this stuff that's really complicated, lots of different colors here, we're seeing many, many different ages of rock squashed up into one small area, which is what we get during mountain building events. Okay, so that's kind of you can see a much bigger, go to this website if you want. I don't think that's a link, but just copy and paste. And you can see the entire map of the whole United States. It's very, very cool to see what ages of rock, what kind of rock are just in different parts of the country, which is very special. Okay, so so now we're continuing. We have our Grenville orogeny, and now what's happening is the Appalachian area became kind of what we would call passive plate margin. So not a whole lot as far as plate tectonics going on. Very similar to what's happening today on the East Coast of North America, where there's no current mountain building. So basically what's happening today isn't the first time the Appalachian area has been born. It's done that before. So, but it was periodically submerged below shallow seas, so sedimentary rock just kept building up, and building up, and that's kind of cool. So where are all those bodies of sedimentary rock? Well, eventually we start to get more mountain building, so that stuff gets squashed and metamorphosed into some more Appalachian mountain stuff. So we don't have all these sedimentary layers, bodies and bodies and bodies of sedimentary layers in North Carolina and Virginia and Maryland and other places along the eastern seaboard. They've been squashed and squished up into the mountains, and they've been metamorphosed. So instead of things like limestone and sandstone, we have marble and quartzite, and a lot of the marble and quartzite that we see in the Appalachians, as well as other metamorphic rocks, are from the metamorphism of shallow sea sedimentary rocks from this time period. Okay, now during the Ordovician, the time period where our local rocks here in Cincinnati were deposited, we're starting to get some action occurring again. We'll see a picture of that in a second. Where we start to get another body, or an oceanic plate called the Iapetus plate, and this is going to be called the Iapetus Sea, and it's going to begin to sink below the east coast of North America, essentially. And so we have a new subduction zone, and the early Appalachians begin to form, kind of like what we're predicting is going to happen in the future that I mentioned a little bit ago, that deep, that oceanic crust becomes really dense and it sinks deeper and deeper. It can begin to create a subduction zone. It's happened before, and we think it may happen again. It'll be a while, but so because we have a subduction zone here, not just a continental collision, but subduction zone, that means we're getting melt and we're getting volcanism. So these, so our Paleozoic Ordovician age Appalachians were volcanic. So here's image 1 here, where we're looking at, so Laurentia, this is going to be basically the eastern seaboard. So Cincinnati would be down here, might be below the surface of the sea as well, I'm not sure. But this is essentially what's going to end up being North America, and these other areas will become other things. But so the Iapetus Ocean, and then with more heat, or sorry, with more dense rock, dense cold oceanic rock, this begins to sink down and begins to create a subduction zone. And that's what's going on with picture 2, where we have some subduction taking place. Baltica, Caledonian Highlands. Caledonia basically is the Roman word for Scotland. So the Caledonian Highlands are going to end up creating much of the British Isles, including the Highlands of Scotland. But we have some subduction taking place, so the Iapetus Ocean is going to completely close as this oceanic plate dives down below Laurentia. Again, this is North America. We're creating now the Taconic Orogeny. So we had the Grenville orogeny. Now we're on to the Taconic Orogeny. We've got 2 more to go. As this Iapetus Ocean is closing, Baltica is getting closer and closer. So basically what was Scotland and much of Asia and Europe is going to collide into North America. So we'll see that next. So mountain building continues throughout the next 250 million years. So other continents, including that Baltica, were thrust up onto North America, and Pangea is starting to take shape. So that North American craton we saw was called Laurentia. Once we add Europe to it, we call it, and Asia, I guess, we call it Laurasia. So Laurasia is going to combine with the southern continents, Africa, South America, Antarctica, India. Those are going to be called Gondwana. They're going to get together. So we'll see that in a picture in a second. So by about 300 million years ago, finally the southern continents, called Gondwana, here which is called Africa, is getting into the North American craton. They're going to collide, this time not in a subduction zone, but in a continental collision, kind of like the Himalayas today. So this is going to create our most recent supercontinent called Pangea. What's my dog doing over there? She's hungry. I haven't fed her yet, so she's starting to get goofy. Hi, Brandy. Hi. Okay. Yeah, I know you're hungry. Okay. Anyway, but we have 2 orogenies down. We've got 2 more to go. So getting there. So this is where Pangea is mostly being built here, as we have Africa and the other southern continents collide with Laurasia, essentially the northern continents. So here's a picture of that. So Baltica then has collided into Laurentia, creating the supercontinent of Laurasia. And antler highlands, these are going to end up being, we find some of the antler highlands in Nevada. So now we're starting to kind of think about maybe forming the Rockies, the very first baby steps of the Rockies. But check out what we're focusing on is the Appalachians. Here we go, the Acadian highlands. So the Acadian highlands, we can still see a lot of these rocks up in Maine and some other places called the Acadias, the Arcadias, things like that. So we're really creating more and more of the Appalachians. Cincinnati is going to be in the, we were above sea level, but getting like, kind of river deposits. So Cincinnati, actually, northern Kentucky, all of Kentucky, would have been bathed by rivers draining these Appalachian mountains. And these rivers made it all the way to Alaska. So one of the videos that you'll see that I have a link to, I hope you watch it because it's actually taught me a lot about this stuff too. We actually know, and we could do research in Kentucky, in eastern and western Kentucky, and see those red sandstones and tell the direction those rivers were flowing in. And they weren't flowing north to south. They were flowing essentially to the west, maybe slightly northwest, and they were dumping sediment on top of what would end up being Petrified Forest National Park in Arizona. So these early Appalachian mountains were eroding even back then. They were getting taller and taller, but erosion is constantly going on. And those rivers were going to dump sediment as far west as Arizona. So I think it's pretty cool. We always think about rivers going north to south, and that's not the case in many cases. And if we go back through Earth history, it hasn't been even in our region. Finally, Pangea comes together. So Laurasia, Gondwana, I know I've been saying those words before. I didn't have them written down, but here they are. So the northern continents, yeah, Siberia is going to catch up as well in there. But we have North America, much of Europe and Asia in Laurasia. Brandy. She starts kind of barking at me when she gets hungry. Now she's going to come over here and start pawing at me and barking. You might hear her bark. She's something else. All right. Gondwana are the southern continents, Africa, South America, Antarctica, India, Australia, all those guys that seem to start with A mostly. They're going to come up here and collide with Laurasia. So we finally have the central Pangean mountains forming. There is a continental collision, so this is a Himalaya-style collision zone. So we know at one point the Appalachians were at least as high, if not higher, than the Himalayas, which were only formed by one of these events. But the Appalachians were formed by, so far, a continental collision, a subduction zone, another subduction zone, and another continental collision, and to create what we see. Okay, so a little review. I'll definitely get rid of my face for this one. I like this because this really just shows everything in a nutshell. It's very cool. So our Grenville orogeny and then our rifting. Remember, going back to our Wilson cycle, we've got a big continent here, a lot of heat welling up underneath of it. And so we start to get rifting as we have these pieces. I don't even want to draw on this really. It's already got everything we need. Check out these arrows here. As these pieces begin to pull apart. Then we have our passive margin, kind of like what we see in the East Coast North America today, where there's no active plate tectonics going on, but we have some continent, some island arc over here, which we know that because some of the very ancient Appalachians have some evidence of ancient oceanic volcanic material that would have been thrust up onto the continent during this time. So that's moving closer and closer, and it finally thrusts up on there, creating the Taconic highlands and the Taconic Orogeny. This is our exotic crust. That's going back to Baltica. So now, though, that passive margin turns into a subduction zone because this is that oceanic crust that gets heavier and denser and sinks and begins to form a subduction zone. So Baltica, much of Eastern Europe and some of Asia, is going to move closer and eventually collide, and that forms the Acadian Orogeny. And here we go. Here's Gondwana, which is called Africa here because it's largely that, but all the southern continents. And they finally collide, and I didn't mention this word before, but the Alleghanian Orogeny. You may have heard that word. The Allegheny is a region in Pennsylvania and much of the Appalachians. And this is going to form our big old continent. It's kind of like the Himalayas today, where we have a continental collision. Okay, and the part of the story I didn't get to quite yet, but here we go. We're back to the beginning of our Wilson cycle, where we have a big continent, a big, massive, very thick interior, where, okay, there's mountain building going on, but once that stops, well, then what? There's some ideas as to how this begins. First of all, we think that heat does build up under this and really doesn't have much of a place to be released because this continental crust is so dang thick and doesn't really allow heat to go through it. So we can start to get some rifting forming as these plates are beginning to spread apart. Or, and it's not like rock is bouncy at all, but think about a bit of a rebound too. This stuff has been colliding together. Once that momentum diminishes, then, well, maybe it could start to bounce back the other way, you know, so we could start to get some rifting because of that. Either way, eventually we start to get, well, okay, with the Appalachians, we're not there yet, but with the Appalachians, we have what's today looks a lot less impressive than back when it was more like the Himalayas or the Grenville Mountains. We have some very special types of mountain building. We've got the valley and ridge. We have the Piedmont, which is going to be some of the most deep-seated, highest pressure rocks forming. We have the Blue Ridge region. So we have, which is a very tough unit of rock that has been squashed up in here. So there's a lot of different parts of the Appalachians, not just the Appalachians, but that's true of the Himalayas and other mountain belts as well. Certainly true of the Rockies. So I also bold-faced our important orogenies here. So definitely want to know about them. So you definitely want to know what is happening to form those orogenies and around when they formed as well. Okay, so during the Mesozoic, again, Pangea is beginning to break up. It breaks up beginning about 220 million years ago during the very late Triassic. And so we have a new passive margin born. And this means that where that on the East Coast of North America, where there used to be all this mountain building to form the Appalachians, now we really don't. So this process was stilled. It kind of stagnated. And that's why here in the eastern part of North America, there's no current plate tectonic boundary. To get to the eastern edge of the North American plate, not the continent, because that's just right there off the coast of, you know, the eastern seaboard. But to get to the edge of the plate, we need to go all the way to Iceland and the mid-Atlantic ridge, right? So right now, the edge of the continent is in the middle of a plate. That means there's really no active tectonic activity. That's what we're seeing. There's been a lot, because there hasn't been uplift, instead there's been weathering and erosion. So the mountains are being worn away. By the end of the Mesozoic, the Appalachians were almost a flat plain, but during the Cenozoic, we had some uplift. This was partly due to, it was partly related to glaciation. It was partly related to, a lot of places experienced uplift, and we're not exactly sure why in a lot of cases. But what happens is think about the Grand Canyon. Let's go somewhere else. Think about the Grand Canyon for a second. The reason why the Grand Canyon is so high, you know, going from the top where you actually, you know, stand there and see the thing all the way down to where the Colorado River is carving out, is because of some of the processes that form the Rockies have also thrust up Utah and much of the western states. So it's kind of like taking a saw. The Colorado River is kind of like taking a saw down through this big body of rock that's been uplifted. You can't carve down through something that is already very, very low. Rivers don't really very aggressively affect that. But once you start uplifting something, rivers will cut away at it pretty aggressively, and that's exactly what's happening during the Cenozoic to the Appalachians. They're being uplifted again. Nice, gentle uplift, but still. And so rivers are cutting away at them pretty drastically, carving the nice rounded hills that we see. So they're also carving down into kind of making some canyon type of forms, you know, some really cool things, but they're carving into some of these really ancient folded, very high pressure metamorphic rocks. And that means that we're able to see these right at the surface. You can see them alongside the road, right? If you drive through the Blue Ridge Parkway, you're seeing, garnets and very deep, very high intensity, high temperature metamorphic rocks right on the side of the road. And those didn't form anywhere near the surface. They would have formed super, super deep and are now exposed from this process of uplift and erosion. Okay, so Pangea is breaking up, and so we're starting to form the mid-Atlantic ridge. We're starting to form the Atlantic Ocean, kind of like the East African, actually very much like the East African Rift Valley is forming today. But this is older, and it's happening. It's a split apart, not Africa, but Pangea. So we're unzipping down between North America and Asia, unzipping down between Africa and South America, and continuing south. And that's what's happening today, is the Atlantic Ocean continues to spread wider and wider and wider. That process began here about 200 million years ago in the breakup of Pangea. Okay. And the Appalachians are being heavily, heavily eroded. So Cincinnati, right about there, we don't really have any record in Cincinnati or northern Kentucky from this time period. Nothing, we don't really have Mesozoic rock here. It's all older than that. But our Appalachians, instead of those nice tall mountains that were like the Himalayas, are now becoming our rounded, smooth, beautiful mountains that we see today. Layers and layers and layers going back as the eye can see. So it's just a very different kind of mountain belt. But what we're seeing with the Appalachians is the fate of even things as tall and impressive as the Himalayas. So the Himalayas today are like this, and we can probably, actually with seismic imaging, we could identify some of these fold and thrust belts, some of these metamorphic rocks by using density studies, stuff like that. After enough erosion takes place, though, we have the Appalachians and this kind of tongue of rock that is very dense, that has been kind of broken and then thrust up over the rest. You'll see that in one of the videos. This is very resistant, very hard, so it sticks up pretty high above the rest of the mountains, and that makes the Blue Ridge, because it's a ridge. We have the Piedmont, which should be this area here. We have the Valley and Ridge Province, which is going to be all these fold and thrust belts, a lot going on. But eventually, give it another 250, 500 million years, something like that, we end up with something like the Canadian Shield, which last had its big orogenic process during the Grenville. That was the last time it really experienced a whole heck of a lot, is during the formation of Rodinia. So it's been, the Appalachians have been eroding and weathering down ever since Pangea stopped forming. The Canadian Shield has had 500 more years to erode than that, because it stopped forming. These mountains stopped forming when Rodinia stopped forming, which was about 500 million years before Pangea. So yeah, the fate of all of these, even the Himalayas, is to look like the Canadian Shield. I think that's pretty cool. Again, I think the special thing about geology is that, there's a lot of things, but one of them is that we are only here for a short period of time. We're only here studying this stuff for a generation or two. Or how long have we seriously been studying geology? Since 1850s, It's not very long, to 200 years, 250 years. And what we're seeing is quite literally, because not a lot of geological things happen that quickly, we're quite literally seeing a snapshot of what the planet's doing. We're seeing mountains being formed. We're seeing mountains being broken down. We're seeing volcanoes erupt. We're seeing some volcanoes go dormant and never to erupt again. We're seeing rift zones in Africa that are just beginning. We're seeing very ancient rift zones, like in the mid-Atlantic, that have been going on for 200 million years, 180 million years. We're seeing the very beginnings, the very first whisperings of crustal extension in the state of Nevada. So we're seeing these processes, the same processes, but we're seeing different stages of them during our one little snapshot of time that we have here to study this stuff seriously. But because of that, and that's very special, I think, we're just around for a very short time compared to the Earth. I hope you're getting that concept, if nothing else in this class, I guess. But because of that, we're able to make sense of all those things and tie them together and see what the past was like. how did the East African Rift Valley begin to form? How did the Mid-Atlantic Ridge begin to form? How did Pangea begin to break up? How did the Appalachians begin to form as we're seeing the Himalayas continuing to form today? And that's pretty cool. So anyway, that's about it for the Appalachians.